Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Abstraction refinement is been used for proving safety properties for programs, might involve solutions on SLAM. Byron's going to show us that it's also good for doing termination.
Thanks. All right, so this is work that I think many of you will know Andrey and Andreas. So Andrey interned this summer at Microsoft Research in Cambridge, and Andreas is a visiting researcher at Microsoft in Cambridge. So this is a bit of code from the serial enumeration device driver. And this code, it has a loop. So here's the beginning of the loop, and here's the end of the loop here. And this code, it goes around and around, and it's calling other device drivers, other serial-like device drivers. So that's happening here. So it creates a request. It calls the other driver, some other thing that sort of responds to the serial protocol. And then if this other device driver, its dispatch routine, returns a status that's a success, so we don't go into this case, then we take some information out, we dereference a pointer, go to a field, take some information out, and increment a value pointed to by this pointer, and then go around again. And we keep doing that until this thing exceeds buf length. And so this is code that's executing at kernel, high priority. And it's causing bus activity, right? So you have high kernel level execution bus activity, taking locks perhaps. We don't know what this other dispatch routine is doing. And it's actually possible that this thing could spin forever. Right? And the reason is that if the device driver that's being called returns success but doesn't return a positive value, then we'll just keep spinning forever and ever. Okay. So this is a really bad situation where we have a reactive system, like an operating system or a mail server or a web server, and it's using a component that we expect will always terminate. Right? So this bit of code that we're calling, this is a dispatch routine from the serial enumeration device driver, and we're expecting when we call it, it should always come back. And if not, then this code, not only will this make the machine hang, and we'll sort of lose maybe our serial stack, but furthermore, now we're accessing all these kernel-level data structures at high priority, which will now put the rest of the machine in more pressure in some sense. So now we could actually have other device drivers going into states that they're not used to being in, so we could actually see crashes too. Okay, so this is the idea is we have reactive systems, and we want to prove that the components that they use are terminating. Okay, so I expect that whenever I hit file save, that thing should never spin forever. Right? It should eventually come back and tell me my disk is broken or it's saved.
It's forever.
Yeah.
What's forever?
Forever. Keep going. It's this. Basically, I'm trying to get rid of this hourglass. Right? Forever. That's a different issue. So I'm going to worry about will it be guaranteed to come back? I don't care. Maybe if it'll take 6 months, that's fine with me. Okay. So what we need is to handle this is we need a tool that proves the termination of C program fragments. Right? So I don't really care as much about taking a C program and proving that it always terminates, but I want to take functions and then call them from some context and prove that function will always return. And what we need is to deal with a large program, so maybe 100,000 lines, something like that. Arbitrarily nested loops and recursive functions, and we need sound support for all the stuff you see in C, like side effects, references, function pointers, and so on. Okay.
I don't think Andrey had a good point. So you implicitly expect that if you prove termination, it will terminate in reasonable.
That's right. Yeah. So I mean, another issue is, I mean, if we could take a program and just look at its complexity, maybe it's broken if it's not. If it's exponential, for example, or you could make some soft time guarantees or something like that. But that's not really the problem I'm trying to solve. So why don't we have a tool like this today? And the reasons appear to be that until now, we haven't known how to do counterexample-guided abstraction refinement for termination proofs. And this is the technique that in SLAM allowed us to handle large programs for safety. And we don't have a good method of doing decomposition for termination proofs. So termination is like a whole program property. And when you have nested loops, you end up thinking about all of the nesting in many of the tools I've seen. And then in termination analysis, there hasn't been any work really that I've seen on side effects and functions and function pointers and so on. So, yeah.
Isn't termination of a loop can't be reduced to a safety property? The question that I'm asking is the while condition always true?
Say again? Can you just repeat the question?
Can't you reduce the termination of a while loop to a safety property?
Yes. So that's what I'm going to, well, so what I'm going to do is convert it into a set of safety properties. So maybe I think the answer will be yes, but a set of them, right? Once you have a termination argument, I think you can turn it into a safety property. But then you have to, I think finding the termination argument is not something that you can turn into safety for infinite state systems. For finite state systems, then yeah, there's a paper by Armin Bieri about how to take any liveness property and convert it into a safety property. Right. But for infinite state, I don't think you can once, but you can find a termination argument and then convert it into safety. Okay. And that's what I'm going to do actually. So, well done. Yeah.
It's possible that you could prove that the guard is an invariant of the loop, then you know that it won't terminate. But if you can't prove that, it might still be that it doesn't terminate.
Huh? What? We were talking about proving non-termination. Right, yeah. Yeah.
Sometimes when you execute it, it doesn't terminate, and sometimes it does.
Yeah.
Then you would not be able to prove that the guard is an invariant.
Right, that's right, yeah. So I think that we've now solved all these problems, basically, right? And we have a tool now called Terminator, which is the result of this result. Okay. So what I'm going to do is I'm going to review SLAM, but just very briefly because this crowd knows SLAM pretty well. And then I'm going to talk about how to do abstraction refinement for safety, or for termination. And then I'll show you some examples. Okay. So I'll show you the algorithm that Terminator implements and then show you some examples. So first of all, why can't we use SLAM to prove termination? So it seems this is SLAM, as you know, it has this abstraction refinement loop. So it takes some property and a bit of code and first constructs a new program that converts the checking of the property reachability problem. And then we go through this abstraction refinement. So we take the program, essentially replace every conditional statement with non-deterministic choice. And that's an abstraction of our original program, and then try and prove the correctness of that program in the check step. And then if that check doesn't work out, then we come to the refinement step. We walk through the bug that we found in the abstraction and try to determine if it's a real bug. And if it is, then we're done. And if it's not, then we refine the abstraction. We go around and around. Right, and the problem with this, the problem with SLAM is it's only for safety, right? And in fact, it really uses the fact that we're only proving safety in the abstraction step. That's the abstraction is taking advantage of that fact. Right, so the abstraction step will take programs that are terminating and return programs that are non-terminating. So we're pretty much out of luck trying to prove termination. So for example, you might see while x is less than y, and we'll replace that with while non-deterministic choice. So now maybe it terminated before, but certainly not going to terminate afterwards. Right, and this step, the refinement step, it takes counterexamples and symbolically simulates them, and tries to determine whether or not the bugs are real. And it's expecting that the trace that it's examining is finite. But in the case of termination, your counterexamples are actually going to be infinite. Right? So neither tool really seems to fit very well. Okay, so that's my review of SLAM. So one way we might prove termination of a program is to come up with this magic set R of well-founded relations. Okay? So this is it's finite. So we have im relations, and they're well-founded. And what we're going to do is we're going to take every path through the program that's cyclic. That is, it repeats execution through a program location. And check, first of all, think of that path as a relation. So every assignment statement is like a relation on the pre and post states. And take the relational composition of each of those assignment statements and conditional checks and construct a large relation representing that path. And then make sure that that path implies one of these well-founded relations. Okay, so in some sense, we're saying that for every cyclic path that we have in the program, we can think of that as a relation, and we know that that's well-founded because it implies one of these well-founded relations. Okay, and there's a finite set. And if we can check that, then we've proved the program terminating. Okay? Does everyone believe that? Okay, that's often when I give this talk, this is where people want to stop and talk for a while. So I'll give you a moment to think about it. All right? So this is due. Yeah, there we go. Yeah.
But there's no unaffection. I mean, you're not saying that all other relations are unaffected.
What's that? No, that's right. Yeah. Just take any path from point A around. Maybe it can go through point A 5 or 6 times, back to point A. Unroll that in some sense. And think of it as a relation and make sure it implies any one of them. It doesn't matter which one. Okay, so imagine that I have a device driver and I had some path, and maybe it's revisiting this program location here. So every assignment statement and every conditional check, so this is while star C pointer, I think of it, the assignment statement as a relation, the check as a relation, I take its composition, so this path represents the relation, and make sure that it implies maybe RM in this case. Okay, and I just keep doing that forever and ever. Okay, yeah?
So one path might be included in one of the relations, but might not be included in another relation.
That's right.
You're arguing that it still terminates if you can just show that there's one that decreases?
Yeah, for every path, right? Not for just one cycle around the loop, but any number of cycles around the loop.
If there are 2 different ways around the loop, and one way decreases one of the measures, and the other one decreases the other, you're saying that it terminates.
Yeah, because take the case where we go around and we come back to program location A, and that implies R1. And then maybe if you went around 2 times, it would imply R2. And maybe if you went around 3 times, it implies R4. And then maybe the next time, it implies R1 again, and so on. So we have a finite set. And any number of cycles through program location A, there's a relation. You can think of that path as a relation, and it implies one of these. Then the implication says that it's well-founded.
So in that case, all of your cycles are the same path through. I was thinking that the loop might have an if statement in it.
Mm-hmm.
The 2 cycles that you get. How
yeah, that's right. So you might go A to B and back to A. That might be one way, and another way would be C and back to A. And now I'm going to have the path A, B, A, C, A, for example, and that's a relation. And maybe that one implies R1, and maybe I have A, B, A, C, A, B, A, and that implies R2. And I just do that for every possible one. The idea is that, yeah, there's an infinite number of these, but hopefully we'll have a technique of saying, well, no matter how long it is, I know that it implies one of them.
It's like colors, and by Ramsey there is one color.
That's right. That's right. Yeah, that's right. And the proof of this is by Ramsey's theorem. So in SLAM, the abstraction refinement for safety, we add a property and it's given by the user or someone from the Windows division. Right? And we have we're going to do abstraction refinement. So we have this initial abstraction is essentially just the program control flow graph with the non-deterministic choices chucked everywhere. Right? We throw away all data in some sense. And then we're going to begin trying to prove those abstractions correct. And as needed, we'll add a little bit of information back. And to do that, we'll add new predicates and then reconstruct the abstraction. Okay, so what Terminator is going to do is we're going to, for each important program location, and I'll talk about what that means in a little bit, we're going to have the property is going to be a disjunction of these well-founded relations. Okay. And then we'll have the same initial abstraction. So we'll have just the program control flow graph with non-deterministic choices everywhere. And the initial R is going to be false. Okay. So this is essentially the relation that that you can't imply. Okay, so this isn't going to be a very powerful. Think of this set as the termination argument. We're going to add more and more things to it. So we're going to build up this termination argument. And in the beginning, it's the termination argument that will never work. And so now we have two methods of refinement. The one method is to, like SLAM, to add new predicates. They're slightly different in some cases. We're going to generalize that just a little bit to something called transition predicates, but it's essentially just like in SLAM. And the other method is to add the R, to add a new disjunct to R. Right? And so think of a path, think of a counterexample as a lasso, where you have the stem and the loop and the Honda is here. For any of you cowboys, the Honda. Right? And we're basically going to take paths that look like this and try and find their sort of witness for being well-founded, and we'll chuck that into the set R. Okay. Oh, and Sumit, this can be encoded as a safety property. Right? So the trick is finding the set. So if someone magically gave you that set, then yeah, you could turn it into safety. Okay, and this will be done via something called rank function synthesis. So there's been a recent set of papers about how to take an unnested while loop with only linear arithmetic updates to program variables and to automatically compute a ranking function for that loop. And we're going to use this technique to construct the things that we put into R. Okay, so Terminator to date seems to handle in cases for device drivers, dispatch routines of device drivers, like 10,000 lines. Okay, so we can take a dispatch routine from a device driver, or for any device, just take the device driver, and it essentially goes through all the dispatch routines and proves that they always return or finds counterexamples for 10,000 lines. And it handles, although we don't need them, recursive functions, arbitrarily nesting of recursive functions, though you don't see that in device drivers, but also arbitrary nesting of while loops and for loops and so on. And because what we eventually construct is something for SLAM to check, right? Where I'm going to compute a safety property and then check it with SLAM. Then whatever SLAM does for function pointers and side effects will be handled by SLAM. So this is Terminator's algorithm. Okay. A couple of you have seen this talk, but this is new. So Terminator takes a program, P, and the first thing we're going to do is we're going to compute this important set of program locations. So essentially what we're going to do is we're going to find a set of program locations such that if we prove for each one of these program locations that the program can't visit that program location infinitely often, then that implies termination. Right, so we could do actually every program location, but that set's too large. Or we could do it at every call to a recursive function, for example. And there's sort of different choices. But essentially what we want to do is we want to take termination, program termination or functioning termination, and convert it into something like a local termination property where for a certain set of locations, and we'll try and keep that set small, we're going to prove that you can't infinitely often pass through there.
That would be just the loop pairs, for example.
Yeah, it gets a little trickier with recursive functions because you have some choices about where to put it. So you can put it at the call sites or the function body or something like that. Yeah. And then it gets a little tricky with when you have go-tos. Yeah. So you have to. Yeah, that's right. Yeah. So you find cut points and then sort of choose the right ones. Okay. So now we have a set of cut points. Okay, L or C. And so for every location in C, now we're going to do something. Okay. So in the end, what we'll end up with is we'll return this thing here. So L is a set of counterexamples. So for each program location that we've decided we have to prove that the program can't visit infinitely often. If that proof fails, then we will produce a counterexample and we'll hand that back. And so that will be an L. So we'll have a set of counterexamples. And then R is the termination argument for each of those program locations. So now it'll be indexed by the program location. So essentially we're going to, for each L, we'll start off with the R sub L will be false, and then we're going to refine that. Okay, and when we've proved that that this program location can't be visited infinitely often, then that will show up in here in the end. Okay, so that's what I just said. And then what we're going to do is we're going to refine R sub L. Okay. So this step, now we're given an R sub L. So this is the termination argument. This is the program location, and this is the program. We're trying to prove, we're checking now to see if this termination argument implies that this location is not infinitely often visited in this program. And we convert that into a safety check. So we construct a new program with p hat and L, and there's a location called L sub error. And we're going to now prove that L sub error is unreachable in p hat. And if
you say argument, you mean just a relation?
It's right. It's the disjunction of well-founded relations. But it's in some sense the description of why it terminates. So if we can prove that argument holds in the program, now we prove termination.
Intuitively an argument, but formally.
Formally a disjunction of well-founded relations. Yeah. Okay. So we have this new program p hat. And we want to if L error is unreachable, then we've now proved what I'll call L termination or local termination. And if a path is found to L error, that path can be converted quite easily back to a path in P that looks like a lasso. Okay, and then we'll examine that lasso. So, and I'll talk a bit more about what happens. I don't know what to call this, so for now I'm calling it secret sauce. Okay, so now we'll call slam on that p hat. So if slam says that L error is reachable in p hat and it gives us a path, and so pi is some path with a set of transitions, then we might have a bug. We might have termination. We might have found a lasso that we can't prove is well-founded, or we have like a false counterexample, and so we're going to refine it away. So what we do is we take this path and think of this as the relation that path represents. So we take the assignment statements and the conditional checks and construct a relation out of it. And then we try to prove that it's well-founded, and that with this ranked synthesis work will produce a ranking function as a witness to that proof. And that's done via a tool by Andrey Rybalchenko called Rank Finder. So if even though we found a path that violated the termination, our termination argument, but Rank Finder said actually that this path is well-founded, right? So we don't have to worry about this one. It will produce a ranking function, and we'll add that into the set. So we'll construct a well-founded relation from the ranking function. And it's just basically saying that the ranking function is bound by 0 and it goes down. And the details of what this means and how this connects up with the program I'll talk a little bit more in a minute. But just imagine that there's a way of talking about previous values of variables and current values of variables. So it's the variables that are in scope in the path, essentially. Okay. So I'm being a little bit vague here. Now, if Rank Finder couldn't prove that this is well-founded, now we've found a lasso that we believe is a possible infinite loop. So in that case, we add that into the set L. So we say at this program location, here's a path that appears to be a lasso. Now we're trying to prove termination, and if we have failed to prove termination, it doesn't necessarily mean that it's not terminating. So we might return paths that are not bugs. And in that case, we invalidate the termination argument. Otherwise, if slam said that L error is not reachable in p hat, now we've proved this local termination property. So we found now a set that implies termination. So now it holds, and we go on to the next cut point. Okay? Any questions? No? So here's secret sauce. Okay, so the cut point will be here. And this is P. I have some disjunction of well-founded relations, which is the termination argument. And I want to construct P hat. So I'm going to do a source-to-source transformation. Okay, so this is now P hat. So we're going to introduce a new global variable called copied. So I guess the high-level idea is that we want to construct the following check. We want to let the program say that this is the timeline of some path through this while loop. Right? So at this point, we have state s sub 0, state s sub 1, and so on. And what I want to do is I want to, at any time, at some non-deterministically chosen time, i.e. any time, I want to take a snapshot of state here. And then, so this is I'll call H, of the Honda. And then from any time after that, I want to make sure, so let's take this one randomly. So this is S sub K. I want to make sure that the state here and the state here are in this well-founded relation. That they're in one of them, right? So that is H and S sub K are in the disjunction of R. Okay, and notice that this is any time and this is any time. So I take any time and then any time after that I want to check. Okay, so and I want to construct a program that when I run slam on that, that's the result I get. So this choice is this time is non-deterministically chosen, right? And I need to record when I've taken this, when I've latched this. And that's what copied represents. So copied will be initialized to 0. And so every time around the loop, slam is now going to check this property. So if we've done the copying, so that means we're now past here, then we want to check that R holds. Okay, so that's just making sure that one of these relations holds between this state and the state. And if we haven't copied, then maybe we want to latch it now, or maybe we don't, right? So if we don't, then we go to here and we go to here. So effectively, we've done nothing. But if we take this choice now, then I'm going to copy, in this case, x and y, into some new global variables. Right? So if I copy x and y, then I'm going to create h of x and h of y, and copy them over.
So this is the effect of checking all the transit closures.
Yeah, that's right.
Yeah, that's what's the
Yeah.
And so R presumably is referring to h of x.
H of x and x, yeah. Yeah. And so the counterexamples you'll get will involve also h of x and x. Right?
So assuming no nested loops.
This works because we're just proving that this program location isn't infinitely often reached. So if there are loops, or maybe it's recursive, that's a whole different issue, right?
But it's copied. Is there only one global variable copied, or one for each loop?
We could ideally do it. We can create a program for each loop. So just one copied for the whole program, because we're only checking one loop.
Cycle one. You're just checking one cycle at a
Yeah.
time. So that's why you deal sort of naturally with nested loops. You check all.
Yeah. So slam, if this function doesn't terminate, slam won't find that bug in this case, right? Because we'll get past here, we'll be fine, and we'll just get stuck in here, and slam will compute the fixed point and then say, oh, now we don't have to worry about it. Now we know that this thing isn't reachable. But that's okay because we'll have a cut point that we'll check later on for this function too. Right, so we're just proving that we can't infinitely often reach here, and if the program doesn't terminate because of f, then we're still not infinitely often reaching here. Yeah. And if we are in a situation, like in this case, we are in a well-structured program, then we can actually shut off copy to here. So that means we won't have to worry about the case where we come into the while loop, we spin around a couple times, and maybe we pop out, do something else, and come back here. With gotos, we have to consider that case. But in a well-structured program, we don't have to worry about that. Because there will be another, if there are loops outside of this context, we'll actually prove that that thing can't infinitely often execute also. So we don't have to worry about this loop being, for us, coming in infinitely often. Okay, and then this is the stuff I haven't now talked about. So we have some path, pi, and we think of it as a relation, and we want to prove that it's well-founded. Okay. And I will talk about it very briefly, but if there's time or if people want to hear more, I have to have some extra slides about this. But I'll just say really briefly that we have some path now through the program, and this has been found in p hat by SLAM, that appears to be non-well-founded. Right? So we know that in is greater than 0, im is greater than 1, count is equal to 1. So these are relations, right? This is a relation, and so on. So this is the stem, and this is the Honda, and then we come back around, and then we have the loop. Okay? And there are various tricks that we can play. We can think of this as a relation. So this represents I and j when you go into the loop, and I prime and j prime represent the values of I and j after an iteration of the loop. So that's a relation. Here's the conditional check, the first assignment statement and the second assignment statement. And so this is the thing that we're actually trying to prove is well-founded. There's some tricks to be played if you have pointers, right? If you had I, arrow, x, or something like that, you can actually, what we do is we introduce new variables and then map those locations to mathematical variables up here. But anyways, in the end, we get something that looks like this, and we want to prove that this is well-founded. And there's this tool, rank finder. I won't tell you about it right now, but essentially it automatically can prove the well-foundedness of relations that look like this. And in this case, rank finder would produce this as the rank function. This is the bound, and this is the thing that it's going down by. So it'll say, here's a rank function. It goes down every iteration by 1. And eventually it will hit 1, and in that case, then this will exit. Right, so think of this as the abstraction of the proof of the well-foundedness of this. Right? So we know that every iteration, the transitive closure of this loop is well-founded. Right? So this is so now we need to construct a well-founded relation. So there's a formula here. We take rank and plug it in here and here and here and use D here and here and B here. Right? So we basically just say that rank will eventually hit B and the rank goes down. And then we substitute in variables. So this is what we get. And this is the thing we actually add into R. Right? So this is saying that if you take I, in this loop, if you take I and subtract j from it, eventually it's going to hit 1. Right? And when it does, it exits, and we notice that this is going down by 1.
So you said rank finder works in this case.
Mm-hmm. So it's complete. It'll always find a ranking function bound in decrement if the argument is in the reals or rationals. It's not guaranteed to find it in the integers. And it's certainly not guaranteed to find it if really what we're talking about is walking down a linked list or something. So I'll talk about that in a little bit. But
some decision procedures.
Yeah, we need something else in that case. But I haven't seen any cases where it didn't find one because we're in the integers. So the reals, in practice, the reals are fine. But it's guaranteed to find it in the reals or the rationals. Okay, so now let's look at some examples. So, so you run Terminator, and you get two things. You get a set of bugs, so a set of lassos, right? And you also get, for each cut point, you get a termination argument, and we can look at that. So based on static driver verifier, I took the bug viewing tool and made a modification to it so you could also look at the termination arguments that are produced. So after you've run Terminator, you can start up this window, and you can, in this case we only have one, but if there are multiple cut points you can check, you can click on each of the cut points. So in this case, this cut point was at program location 6 in this program, and this is the termination argument that was found and then SLAM eventually proved. And this is saying this is a disjunction, so these two things are both true. Right? And this is saying basically that x is bound by 100 and x is going up. Right? So take any slice through the transitive closure of this thing, right? So run it as long as you want and look at x, and it will always have gone up by at least 1. Right? So that implies termination. Oh, and notice that the termination argument is only over x and its old value of x, and not p. Right? And so that's very nice, where we are able to sort of separate all the pointer stuff for the termination argument. Right? When we found a path that appears to be non-terminating, it was found by SLAM, which handled the pointers. We get that path, and we don't really have to think about pointer aliasing in that particular path. We know all the pointer aliasing relationships, and we can find a ranking function sort of separate from pointers in some way, and then we produce that, and then SLAM again checks it in the presence of pointers. Now it may be that star p shows up here. We could have said star p is bound by 100 and star p always goes up, but either way it doesn't matter. So x and star p, either one. So here's Ackermann's function. So this code, it's setting, we have two variables x and y, and they're non-deterministically chosen, so we're essentially doing for all values x and y, and we call Ackermann's. And now we have 2 cut points. So we chose in Terminator not to choose this as the cut point, but actually to choose all the recursive call sites as the cut points. And that's a bit more work, but it turns out you know a little bit more here than you do here when you're trying to prove termination. So we can look at each one. So essentially we want to know, why are we not going to visit this location infinitely often? And here's the reason. So y is bound by 0. Right? And you can look at it and figure out why SLAM says that's true. We wouldn't be here unless y were greater than 0. And it might have gone down 1, so we know it's greater than or equal to 0. But we know it's not less than 0, right? And that's a safety property. And it also says, look, y goes down, at least 1. Okay, and that's true, right? And the other cut point, x, in this case, x is bound by 0. Right? And you can look, why did SLAM say that? Oh, right. We wouldn't be in here unless x were greater than 0, and x might have gone down. And x always goes down by at least 1, and that's true also. Now, it's harder to think about the transitive closure, but SLAM also checked, what if I go through this 18 times or 20 times? Or what if I went here, 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 here? It still is checking that x is bound by 0 and x has gone down by at least 1. Here's a case where I've taken Ackermann's and I've commented out this x minus minus. So in that case, it produces a path. And so essentially, we choose some x and y, and we call Ackermann's, we call Ackermann's, we call Ackermann's again, and we've gotten to here. And we're basically going to, at the next step, call Ackermann's again. And the argument is that this call, we're in the same state in this call to Ackermann's as we were here. Or maybe here. Sure. Right, notice that the stem could actually include calls to Ackermann. So we could have a call to Ackermann, and at this point we latched the value, and maybe we ran around a couple more times. So here's kind of an interesting case. So this is this loop, because I happen to know we don't know what G does. So what SLAM treats that as a function that could return any value. So in this case, we don't know that this loop is terminating, right? Because Y is going up, but K could go up faster. So Terminator has found a counterexample where we've gone around the loop once, and we don't, it's maybe K has gone up as fast as Y. But this loop, it has proved terminating, actually. Right? And that's because SLAM, when it was proving this cut point, it only considered cases where we got out. And that's sort of back to that nesting. This is I think, a very nice feature where when we're proving the termination of this loop, we don't actually consider the termination of this loop. And that's why we can have 85 nestings. It doesn't matter.
That's a question about that one.
Yeah.
If you don't have the code for G, you are assuming then also that G does not call back into main.
That's right. Yeah, that's right.
You do that for all functions that you don't have the code for.
Yeah, that's right. Yeah, that's true. Yeah, and when we're assuming it's non-recursive, right? I mean, we're assuming it doesn't call anything. Yeah, not just me. So here's a case where we have a disjunction. So at this cut point, we proved that this holds or that this holds. And this is saying that either, essentially, X goes up or Z goes down. Okay. At first, I had just this. Right? I didn't have this case. And then I was trying to make a case where it didn't terminate, and I added this thinking that would do the trick, but actually this program terminates too. I don't know if you see why. Essentially, the case where if X went up and then we decremented X, now we know that Z's gone down. Right? So somehow to keep X stabilized at a value, you're going to have to keep executing this side, and so eventually Z is going to go down past 100. So it's a bit of a brain. Yes.
What if you change that to change the X minus minus to X get non-dit? It's also less graphical order.
I think it's still okay because you're still going to decrement Z each time you do that.
It is okay. So
yeah. After the talk, we'll run it and see. Okay. And this is another nice thing. Notice that when we're proving the termination of this loop, we need to know, so here's the termination condition it came up with. It's saying basically that X goes up. But just looking at this loop, you don't know that that's actually true, right? Because what if Y is negative? So what we actually do in Rank Finder is we first try and prove that some path starting from here and then back around is well-founded. And if we can't do that, then we actually take the stem into account. So we say, well, we knew that when we got here, at least in this case, that Y was greater than 0. So why don't we say that X is going up? And then we add that. It's not unsound to put something here that's not true, because SLAM won't be able to prove it. And in this, it's an invariant that if we're at this program location, that Y is greater than 0. So then it holds. So in some sense, whatever invariant you'll need, SLAM is going to find it. And that's actually very powerful, right? So in termination proofs, that's very unusual. But often termination proofs fail because, we need to know Y was greater than Z and so on, and then you have to go back, try and prove that, and then come back and then try. And now we know this extra information, and then try and prove termination again. But somehow we magically get it because we're converting things to safety, and we consider we're actually limiting the paths from things that start from main. So we're restricting ourselves to the reachable states. So really, when I say we'll take any H and take any SK, I really mean, oh, and by the way, they also have to be reachable. And so that gives us a little bit more power. Yeah.
Are these tools aware of the limited size of integers also?
So
if I have y greater than 0 and then I increment,
yeah.
Does it assume that it's always positive, or it may become eventually negative?
My glib answer is that it's whatever the safety checker implements. And in our particular case, SLAM assumes that everything's arbitrary length integers, and that you could actually. I've done experiments where I've changed SLAM to respect fixed bit widths, basically, and you could do bit operations and so on. So in some sense, we're constructing a termination argument, and we're just saying whatever, let SLAM handle it. So I could put in some other tool that handles, whatever semantics it wants. But of course, the rank finder is also assuming everything's arbitrary length too, right? Because if I tell you more about it, it's essentially doing LP. So we construct this an LP problem and try and find a satisfying instance, and that's assuming arbitrary length integers. So it could be that it magically finds a termination argument that holds, but the tool might sort of keep finding things that it thinks are true, and the SLAM keeps saying no, it's not true. So I'm not sure if things would work, but so to really do a good job, we would need to make SLAM respect arbitrary fixed width integers, and also make sure that rank finder respects the semantics too, and I haven't done that. So this is the case in the Suriname device driver that I was telling you about. So I ran this in static driver verifier, and so it found a bug starting from main in the model of the operating system provided by the static driver verifier product. And after essentially 2,500 steps, it got to this location and then found this bug where we were not checking that the thing is greater than 0.
How long did it take to run?
A while, so like an hour, something like that in this case. Yeah. So, and I'll answer that sort of in more detail now. So I tried some experiments on 23 device drivers. And here, this is a graph of the number of lines of code in the device drivers. So I've removed the names, but for this crowd, I could actually have left the names of the device drivers in. But those of you who know the device driver samples, as few of you will know sort of what these device drivers are, probably. Like serial and parallel port, right? So this is the number of lines of code, and this is the cut point size for each of these device drivers. So we have, in the worst case, we had something like 75 program locations that we needed to prove termination of. In serial or parallel port, I'm not sure which one this is. And so on average, we didn't really have too many, maybe, I don't know, like 25 or something like that, program locations to prove that device driver's dispatch routines always return. We have to prove local termination of each of those cut points. Yeah. It's for loops, it's the beginning of the loop. For function calls that we have decided could be recursive, it's the call site. And for gotos, it's the location of the goto.
Like in any graph, a set of vertices such that any cycle contains at least one.
Yeah. Yeah. So we found a couple of real bugs. I also put in a couple of bugs to make sure I was finding something reasonable. So for each device driver, here are the real bugs, the bugs that I've talked to people in the kernel team and they've said they look real to them. So in one case I found 2, but I put both of those in actually. But in a couple, I think 3 of these are real. And then this red bar are the false bugs. So these are bugs that Terminator gave me, and I looked at them, and it was clear that they were actually terminating. And in these cases, it came down to fixed width. So they're actually doing some bit masking. And SLAM doesn't doesn't handle bit masking very accurately. So in those cases, it was reporting that it was non-terminating, but it really was. And in another really very common case is the case where it's walking down a linked list. And so it just can't find the arithmetic argument for termination. It gives up. Now, there were some cases in the environment model I was able to add some counters. So for example, if you have a stack or a queue and you're removing things from a queue, then assuming that we're not executing concurrently, then actually if you keep pulling from that thing, then it'll eventually terminate. And so I added counters to the APIs. So here are the runtimes. There's actually two sets of runtimes because they're wildly, wildly different. Okay? So in many cases, it took between 70 and 20 minutes for a device driver. Okay, and then in a few cases, it took 2,500 minutes. So, I mean, those are pretty extreme runtimes, but there's no tool to date that could do anything, right? I mean, there's tools that can find bugs, but there's no tool that can find a termination argument and prove it. So it seems reasonable to wait 2 or 3 days to find that termination argument for our device driver. To me, right? If I'm writing a device driver, I don't mind running this over the weekend.
Byron?
Yeah.
So how big did the set of relations get?
That's a good question. So in the small, interesting examples that I run Terminator on, those relations, there'll be 2 or 3. In these, there should only usually be 1. The disjunction should only usually be 1. But sometimes what you get is rank finder does a bad job of guessing. So the particular loop is actually sort of a red herring, and it adds it, and then there's another one that sort of that subsumes the original one. So you do see cases where you have disjunctions. But I can't imagine that device drivers are really doing, they're not implementing Collat's function or Ackerman's functions. I wouldn't imagine that in most cases it was because Terminator sort of misguessed what the thing was and had to come back. So yeah, there's no recursive functions, and I think many of the loops are very simple. Right? So in fact, one optimization we did is we look syntactically at the loop, and if there's a for loop, I can kind of guess what the termination argument is going to be right away. I add that, but then I have to check that because it might be that the thing that the for loop is going over I is maybe passed by pointer and scrambled in some particular weird case. We have to make sure that termination argument actually holds, but it's pretty easy to guess what it is in those cases. And also for while loops, you can look at the control flow, the basic block just before and just after, and sort of dig around and try and figure it out. And so that we actually do that. And that actually made performance much better. There's the other special case that if you only have one disjunction, then you actually don't need to prove it over the transitive closure. So you only need to check one iteration of the loop. And so that makes things a bit faster also. So that's actually very nice for these. If you're expecting that your code is fairly simple and your termination arguments are fairly simple, it'll actually be much, much faster because we don't even have to do the transitive closure. And we only have one disjunction. So we only have to do that refinement loop, the Terminator refinement loop once.
And the main bottleneck is slam.
The main bottleneck is slam, for sure. And the thing is that slam wasn't really built for what we're pushing it to do. So actually I found many bugs in slam where it just had arithmetic. It had unsound arithmetic rewrites, for example. And it's because device drivers aren't typically doing very rich arithmetic, but suddenly with rank finder it is, right? So we're like finding all these arithmetic arguments that slam isn't really optimized for in some sense. Another thing that I'm lying about a little bit is that slam, it has bugs, so sometimes it just crashes. But also there's this notion of where slam can't find a proof and it can't find a bug. And in those cases, I'm lying, but I'm just saying I'm going to ignore that case. Right? So I really should have another bar here somewhere saying these are the cases where slam couldn't find a loop and it couldn't find a proof either.
Okay, if slam is unsound and it does find a proof, how can you trust this proof?
So that's an interesting. Yeah, actually, so one thing that's interesting is that you get this artifact, right? You get a safety property that you can check. So if you had a system that was much slower but more sound, right, then you could actually recheck that with some other tool. So, okay, so what I see the contribution of Terminator is that we now seemingly have a way of building a tool that can prove termination of program fragments, which actually turns out to be important for us as a company, right? We want Outlook always to respond, right? I do. I have a real problem with this. And also, as a company, we have many people contributing the utility functions that we call, right? So in the operating system, we're calling the Fujitsu utility function, and we don't know any the AOL utility function, the dispatch routine. We have no idea what's going on inside of it, or if it's guaranteed to terminate. And our system can now hang, right? And that would mean maybe we're hanging and we're doing all kinds of bad things on the bus. So now the machine's in some horrible state. So it would be nice to know that I don't know what Fujitsu is doing, but I know that it will always come back, right? So we need to be able to handle 10,000 line, 20,000 line programs. So this is new, right? Arbitrarily nested loops and recursive functions. That's new, and something for pointer aliasing and side effects. So you see. There's termination work in pure functional programming and also rewrite systems where they can actually prove much more, probably much richer termination arguments about interesting systems, but they don't really match the sort of things that we write as a company with pointers and function callbacks and all these kinds of things.
When you say concurrency, where exactly do you?
So one thing that I'm assuming is that I have a single thread. Right? So if, for example, I'm a loop and I'm pulling things off a queue, eventually that queue will be empty. But what if there's some other thread that's putting things in the queue? Then I've now said, I've proved that this loop terminates, but it's not actually true. So to really to improve the accuracy or the soundness, I need to model the other threads and what they could be doing. And I can't do that now because what I'm doing is constructing something for Slam to check, and Slam doesn't support concurrent. It assumes a sequential semantics, essentially. But it's not quite as easy as that. So I could produce a program that's something that handles concurrency could check. But now I'm going to get cases where the termination argument appears to be non-terminating, but it's because the other thread that's supposed to do something isn't getting a fair shot of changing some states. We have to add fairness conditions and so on. So I haven't really thought about that too much. So the real thing that I've seen a lot of is heap-based things. So you get this case where you're going around and around in a loop, and every time you're incrementing something by the link, right? So you're walking down a linked list, and eventually you expect to hit some special thing. So what I've been thinking about recently is that we could actually, in this simple case, I could actually do my same construction and call a tool written by Josh Burdine that proves separation logic invariants of programs. So I could actually say, it would actually be able to say, take a symbolic representation of the heap here, symbolically simulate it using separation logic, and you'd get back around, and you would notice that current entry is one step closer towards first entry. So so I actually have given them examples, and that seems to work. So that's maybe something we'll do in Terminator, where if we fail to prove termination in arithmetic, we may be able to try and do something with their tool called Smallfoot. And another thing is that this method is like it's the lorry, it's the Cadillac of termination methods, right? I mean, we construct this safety property and then we do reachability, and it's like the atom bomb method, right? There's actually much faster methods. Right? You could, in the case where we have a loop and there's no function calls, for example, we don't need to do all of this safety, right? We could actually just do some compiler-style algorithms and just make sure, oh, look, you know, there's only one path through and X goes up by one, so we don't need to do model checking in that case. And there's actually a number of techniques that are far faster than Terminator for finding bugs, and they're unsound, but they're unsound cases where you have functions with side effects. But if we know that there are no side effects, it would actually be fine to call them. So that's something to speed up Terminator. And then another interesting thing is to make this work for maybe allow a programmer to express Leibniz conditions. So it seems like Leibniz is often, there's something about termination, like we will eventually get out of here so we can get back to here, and that's why this thing is, you know, I'm infinitely always going to do this thing, whatever the Leibniz property is. So that's all I had to say. Thanks. Questions?
So suppose we neglect nested loops and recursion for now.
Yeah.
What if I take the driver, check each loop, see if it is a random function, there is that loop, and do it for all loops. So is that?
That's essentially what Terminator does in that special case, right? So if you don't have nested loops, it will find the only cut points that are non-nested and prove their termination, right? So in some sense, it's doing exactly what you said. And the interesting question is what happens when you have nested loops? Oh, and it's actually doing the same thing, right?
Yeah. Would it be interesting to also estimate bounds for termination?
Yeah, I think so. Yeah, I've given this talk a couple of times, and this is the question that many people, especially people with systems backgrounds, ask. It's like, yeah, you've proved it terminating, but if a device driver is exponential, we're in a lot of trouble, right? So there should be some program analysis that tells you that this thing will, maybe not some time bounds, but only a dispatcher team maybe should only do 20,000 comparisons, right? And if you do more than 20,000 comparisons, then you're in trouble. Something like that. Yeah.
The last one. Seems any Leibniz properties look like non-termination of a kind.
I haven't thought about this very much, but I'm thinking about operating systems. You're trying to prove a Leibniz property that it will always be there for you, right? And how do you do that? Oh, well, you somehow find a set of local termination properties and prove them, and then somehow you stitch that back together saying, oh, now I know that this loop will always get here. So I haven't really thought about this very much at all, but it seems like I'm thinking about every Leibniz property I would try and want to prove, and I could probably do it by proving a bunch of termination properties. But this sort of not termination of whole programs, but termination of particular function calls.
Leibniz is non-termination.
Right, but in some sense that you would prove that by proving termination of the component pieces, right? So something like that. Yeah, so you could prove a safety property that you never get out. So you would know that you would stay in. But you also want to prove a property that you always infinitely often get back to the beginning of the loop. And to do that, one way would be to prove termination of all of its component parts. So now you've proved that you infinitely often get back to the start. So if you have a polling loop, you can prove Leibniz of that loop by proving termination of its component parts.
And Byron, this implementation you use for drivers, does it have instrumentation for recursive functions? Or it is the same?
Say that.
In theory, you do care about recursive functions. In this practical experiments with drivers, your implementation...
It handles recursive functions, and it turns out that in device drivers it's not going... Actually, it's not true. There are cases where it's going to find recursive functions because SLAM does this pointer analysis, and sometimes you introduce recursion. Yeah, so actually there are cases where I've seen it's proving recursion, and it proves that it terminates, right? Because...
If you disable these recursive functions, then you might get some benefit in sense of...
Yeah.
It would work faster.
Yeah, that's right. Yeah. Yeah.
Isn't it interesting to synthesize preconditions for functions for which it is terminated?
Yeah. Yeah. So you're saying it would be interesting to know what did we need? Like, so you have a termination condition and SLAM proves it magically. Like, why? Like, what invariants did it need? You could actually kind of figure that out by looking at what the predicates were that it inferred. And you could probably dig around somehow and figure out more information inside of the state of SLAM when it finally concluded its argument.
Do you think you can require from programmers to leave traces of their thoughts? You know, I have a loop.
Right.
Intuitively, I know why it should.
Right.
So maybe I should spell it out.
So I was thinking about that. So what if Terminator fails to prove the termination of a loop? And it's like throws up its hands, right? You could actually, this could be actually much more interactive. It could actually throw up a window and say, we're failing to prove termination of this guy, so why don't you tell us why it terminates? And you could put in a relation It could be fairly simple. You could use C expressions, and you would just have a couple places where you'd put in your information. And then it could actually prove that that relation is well-founded, and then check that as a safety property, and then leave that hanging around in a database somewhere. So you could think of this as a termination argument inference engine, and then if that inference fails, then maybe you could ask the programmer for a bit of help. So we also support, in Terminator, you can put a function call right after the start of the loop, basically saying ignore termination. And that's cases to remove false counterexample. It's basically cases where you know the thing's not going to terminate, but you're okay with that. So we're a little bit have already started adding sort of ways for the programmer to express, in this case, I don't care about termination, but you could put other things in there too. Like use this well-founded. You could also say use this well-founded relation, but maybe Terminator would have to infer 3 or 4 others and check them in also. But this is the hard one, right? This is the sort of the main reason it terminates, but there's some other cases I don't care about, and Terminator could figure those out. Okay. Is that it? Thanks.